So, welcome to section number 8. Couple things off the bat. Here's the QR code for attendance things if you want to go ahead and fill it out. I think today's question is favorite study spots on campus or off. Mid-semester meetings, so those of you I met with yesterday, it was lovely meeting with you. I have a lot more meetings lined up for today and tomorrow. If you do not sign up for a meeting and would like to meet, email me, we will find a time. Mid-semester feedback. So we've already gotten about 15 responses, and there are some things that I'm going to go ahead and try to change. So one is I'm being too precious about the annotated section notes, mostly because I want it to be like typeset and beautiful and like fixed, and then it's a permanent resource for the future and everything. Y'all just need answers to things, and so I'm just going to like spend an hour tonight when I get home and like write through all the annotated and then post that. So that will be posted within the next day. Another common thing on the feedback form was requesting the section videos. My policy has been, since I record my sections, any student that asks for the video gets the video. But the reason why it hasn't been posted online, just on Canvas for anyone to access at any point, is because the fear is, especially at the beginning of the course, people won't come to section. At this point in the class, the people that are going to section will continue to go to section, and the people that aren't coming to section will continue to not come to section. And so I'm just going to post those on Canvas so that everyone can see it and you don't have to specifically ask for it. They should be the videos of section.
Oh.
Yeah, because I record section when I do it. I also have the videos from last year, so I will post those as well. So both of them will be accessible on Canvas. I normally upload within like a day or two of the section. If I start getting a bunch of emails being like, the video's not uploaded yet, that's I just need a stable internet connection in 2 hours. So there's that. Extra help room was another one of the things that people want. We are not paid for more help room time, but I will try to offer about 10 hours of extra help room over the next 2 weeks. The next week up until probably Wednesday is pretty booked for me with student meetings and with like some other plans that were already there. And so I'll offer extra 3 or 4 hours on the Wednesday before the exam, and then I'll do a few other shifts the final week of the class. Luke has to miss lecture tomorrow for an interview, and so I'm going to see if he can offer some extra help room hours sometime Thursday through Sunday of this week. So we're trying. It's not something that's in our contract, but we also recognize that you'll need that. So other things that I'm trying to think about. Another one was the fact that the problem set, or not really the problem sets, but more so the practice exams, we just post an answer key. They are not solutions, and that is especially not sufficient when you are trying to use that to learn for the exam. So I've set aside 3 hours on Monday night where I'm going to record a video of me just going through the practice exams and talking through each of the questions. So that will be kind of a resource that you can use. It will not be available until Tuesday morning, but also I don't anticipate y'all to have finished the practice exams until then. Again, the problem set's the big thing. So I read everything on the feedback form, and we try to take it seriously and implement as much as we can. So please fill it out. Please just give some thoughtful responses and let us know how we can make this better. There are some things that structurally we can't do, but the things that we can do, we'll try. This QR code. So if you are one of the people who cares a lot about grades, which it's very fine, if you want to use most of your meeting to talk about grades and what grade do I need to get an A versus A minus or B plus versus B or whatever, this is just a little spreadsheet. Nothing is fancy about it. It's only information on the syllabus. But I just made a little spreadsheet where you can make a copy of it and test out numbers and see what the score is. It's something that very much you can do on your own, but you might not want to do. And so it is just something that you can try out. Cool. I think that's most of my logistical stuff. Are there logistical questions? Okay. Well, let's get into section proper then. So this is the thing I've made for the class that I'm most proud of. This is the alkene reaction web. And it is a lot of information, but I've tried to do it in a way that looks pleasing and that provides some structure. So,
Is that the course color?
yeah.
Oh my gosh, she finally came up. I was waiting for her.
No, yeah. Like I made that. I made that the course cover.
I was like, this is gonna instill some like trauma.
um, but it's color coded where we have some reactions here, and then we have some information about the reaction. And I've tried to group them into little families that make it easier to like study and learn the kind of details about it. But I think the biggest thing that I can do to help you for this lecture is I can give you some like scaffolding organizational structure for these reactions. So the first way that we're going to divide up this big family of reactions is I'm going to draw kind of a line here. The ones to the right over here I call the simple alkene additions. And they fall into these kind of three families, and we're going to spend some good time on each of them because these are the basic mechanisms that you will be tested on for alkenes. They are the kind of prototypical alkene addition mechanisms. The other ones I call complex. And it's because they tend to use like weirder reagents. And also with the complex ones, we don't always give you the full mechanism. So with the complex, you're mostly going to be using those for line reaction synthesis, and you're going to be doing much less mechanism. Like I think for all of these reactions, they've never appeared on a mechanism. The one exception is the HBr radical stuff, which we're going to talk about radical chemistry on Friday. So, yeah. Synthesis line reactions, which again is like half the exam, so. Sorry. No, yeah.
I laughed to like control myself.
You said I laughed, not cry.
Yeah.
So that's going to be kind of our big structural divide, and we're going to spend a lot of time on the simple ones today, and then we'll touch on some of the complex ones. So before we jump into the like first family with the simple additions, we need to get down some terminology here. So for each of these alkene addition reactions, the three things that you should be paying attention to are how that reaction answers these questions of what, where, and how. So what is literally what are the two groups added. So if you have an alkene, you are going to be adding two things, one on either side of the alkene. What are those two things? So for like H2 palladium on carbon, the two things are hydrogens. For like ozonolysis, it's adding carbonyls at those two positions. So it's just knowing what are the two things that you're adding. The where is a question of regiochemistry. So for this, it's like which one adds to which side of the double bond, and we have Markovnikov's rule here. Different books use different kind of phrasings or framings of Markovnikov's rule, but our way, I think, is the most comprehensive, which is that the more electronegative group adds to the more substituted side. More Markovnikov, MMM, the whole thing. Now, your more electronegative group is typically a nucleophile, and your less electronegative group is commonly a hydrogen. But there are examples where that's not true, but this is just kind of the general trend. So if you had this alkene and you were trying to add an H and a nucleophile, your nucleophile is the one that's more electronegative. If you add the nucleophile here at the more substituted side of the alkene, we would call that your Markovnikov product. If you add the nucleophile over here on the less substituted side of the alkene, we would call that the anti-Markovnikov product. That's cool. Sorry, I noticed like all these like small things, like this arrow is too close to this text. Like that's the thing I'm thinking about, and that's why I haven't made the annotated lecture section notes. Yeah. Yeah, totally. So the key for this is something that has more hydrogens on it is less substituted. So between this side and this side, which one has more hydrogens? The right side, so that's the less substituted side. This side over here, we would say is more substituted because it substituted one of the hydrogens for this carbon thing. So that's the, is that?
Yeah, if you don't have a side that's really substituted,
Then,
then we have like multiple.
yes, totally. We would get multiple different regiochemistries. Cool. And the last one is how. And this is the stereochemistry, the relative orientation of the two things that are added. So we have our double bond here, and it's this kind of plane where we have the p orbitals above and below. And we could either add our two things both above or two things both below. And that is what we call a syn addition. The way this looks on a perspective drawing is they would both be dashes, or they would be both wedges. Or if we have the plane of our alkene and one adds above and one adds below, then we get this orientation, which we call anti. And that looks like one on a wedge, one on a dash, or vice versa. So we have the syn and anti dance, which is syn, syn, anti, anti. Y'all are gonna do it in a minute. I'll show it one more time. Syn, syn, anti, anti. Are you ready to do the dance? Ready, go. Syn, syn, anti, anti.
Me during the exam.
It's a thing of like, as soon as I did that with my arms, I never forgot it. So, yeah. Now, if a reaction can get both syn products and anti products, we say that its stereochemistry is mixed. So you're going to get both of them. The last kind of warning here is the letters A and Ti appear in two places and they mean different things. Anti here alone is about stereochemistry. Do they add both on like a dash and wedge or a wedge and dash? Whereas here, anti-Markovnikov is about where the more electronegative thing is added. Cool. So to help you with these three questions of the what, where, and how, outside of each of these bubbles, I've answered the what, the where, and the how. So like these two things are added. Why did I put Markovnikov in quotes if the two things I added are bromines? They're the same. So what do we mean most electronegative? We're just kind of putting Markovnikov because it's normal and it's not something atypical. And then here, like this is an anti-reaction, so that's the how. So the what, where, and how I've kind of pointed out for all of these. Yeah? Both syn and anti. We're going to talk about it. So let's talk about the first family in our simple alkanes, which is the acid additions. So all of these reactions, there are 4 down here, and here are the specific reactions. All of them go through the same general mechanism. Step 1 is the alkene goes and grabs a hydrogen from something. I've written this as HX, where X could be halogen, bromine, or chlorine, or it could be like HOH2 plus, or it could be H2OR plus. So an acid with something else. When it grabs the hydrogen, we have 2 options for the carbocation. Which one is more stable, the left one or the right one?
Oh, right.
So,
The last one.
this one's secondary, this one's primary. So the left one's more stable. The rearrangement can only occur if you're going to make a more stable carbocation. Yeah. So, because this is the more stable carbocation, it is the only one that will occur. You are never going to form this carbocation. So, we add our hydrogen, when we grab this, we add it on the less substitute side here so that we can form that more stable carbocation. Oh, this is a structure thing where I am missing a bond here. Like here, if I was doing the exact molecules, it should be like that, where there's like another carbon here. So, sorry for, again, small typos. But still, one is more stable than the other. I don't know. Then, once you are at this carbocation, then whatever the other thing is, whichever one of these X's, is going to come in and attack the carbocation. And then you maybe have a protonation step, or sorry, a deprotonation step, and then you're at your product. So this basic idea of step 1, you protonate the alkene, make the most stable carbocation. Step 2, a nucleophile attacks the carbocation. That's the basic reaction. Now, with this, we have a lot of stereochemistry that could happen. So, in the first step, we have our alkene here, and we have some acid. So this is going to go and grab a hydrogen. And if, like our double bond is over here, and it goes and grabs the hydrogen on the top, then the hydrogen is going to be on a wedge here. But it could also grab a hydrogen on the bottom, and then it would be on a dash here. In both cases, we're adding the hydrogen on the bottom carbon because this side up top is more substituted. Remember, deuterium is just a labeled version of hydrogen. It's the isotope of hydrogen. And so this thing, it would count kind of like a hydrogen on the bottom, so the top is more substituted. Okay, so we now have these two placements here of the hydrogen. But then, what do y'all remember about what do y'all remember about SN1 reactions with attacking a carbocation in stereochemistry? You can get two different things because our nucleophile could come along and it could attack the top of this MTP orbital, in which case if it attacks the top, then you would get the nucleophile added on a wedge over here. Or the nucleophile could come and attack the bottom of the MTP orbital. They're both equally good acceptor orbitals, in which case then you would have the nucleophile here on a dash. Same thing over here for this bottom one. You could have the nucleophile attack at the top and get this, bottom, and get this. And so if you look at the final products and you highlight the kind of two things that you added of the nucleophile and the H, you are going to get products that are both syn and products that are anti. So that's what we mean by mixed. We're going to get all of these products, these 4 different diastereomer products. Now, do y'all remember a notation that we've used in the past of this like plus/minus? It basically is a shortcut for us to say this molecule and it's an enantiomer. So what we can do, an easier way instead of writing 4 compounds, is let's say we didn't want to write these. We could write this top compound and plus minus, and then the other top compound and plus minus, and that would be equivalent to just writing out the 4 structures. Now this is a lot of work, right? Like these are a lot of answers. This is the most complicated version you could see of this. If you were doing like this alkane and H3O plus, you would have this one product, and this thing doesn't have a stereocenter, so none of this matters. For the most part, on like box problems and synthesis, you are going to be working with the simpler version. For like a mechanism question or maybe one line reaction, you might be asked to do something harder, and so I want you to understand and see the kind of conceptually harder part. So the other thing with the carbocation, other than being able to attack both faces, is carbocations do funky things. We can have rearrangement. So this would go and grab the hydrogen and make a carbocation here. It's a secondary carbocation in addition to a quaternary carbon. We can have a methyl shift because now it makes a more stable tertiary carbocation. And at that point, the OH2 can attack. So your product over here, you've added a hydrogen and you've added the OH, but they're no longer on the adjacent carbons. So like, for example, if you wanted to make this alcohol, you could not use H3O plus because this is going to rearrange. So the warning here is anytime you are trying to do one of these reactions, and especially a box problem or a line reaction, a line reaction or synthesis, you must draw that carbocation intermediate and make sure it doesn't rearrange. So let's try some practice here. This number 1. These are just some problems that I made. They're not in the problem set. Of trying to draw all the possible products with stereochemistry for these. Maybe another like 30 seconds. Oh, happy. No happy. Okay. You can move with it. You can move with it. Okay. So H3O plus, what two things does it add to an alkene? An H and an OH. And it adds Markovnikov. And it adds mixed. Again, for kind of line reactions for alkene additions, I always like writing this, just as a reminder for myself. I know that this is going to form a carbocation, so let's draw the structure of the carbocation. So, which side of the double bond, let's say left versus right, which is more substituted? The left, over here, it has two carbon things, whereas the right one only has one carbon thing. So, that's the more substituted, that's going to be the more stable carbocation, and we'd add an H here. Now, is that carbocation going to rearrange? I mean, we're right next to a tert-butyl group. Why doesn't it not rearrange? It's the most stable you can get with hyperconjugation here, and if you did a methyl shift, then you would just have a tertiary carbocation up top. And so going to tertiary is not getting more stable, so why would the molecule do that? It wouldn't. Okay, the other thing is this carbon right here where we add the hydrogen. Is that a stereocenter? No, because it already had a hydrogen on here. So we don't need to worry about that stereocenter. We only are going to have a stereocenter at this carbocation position, and that's where we're going to add the O. So to draw the product, I would make my OH on a wedge or on a dash, and I would have a plus minus to show that the enantiomer is also formed. So make sure, again, to draw that carbocation intermediate and think through whether or not there is a rearrangement. Okay, for this other one over here, what two things does HCl add? An H and a Cl, yeah. This is Markovnikov, and it's mixed. So, left or right, which is more substituted? For our alkene. The right. And it's because deuterium here, again, it's just an isotope of hydrogen, so it's like a hydrogen on it. Okay, so we draw our intermediate, where we have a carbocation on the right, and we have a deuterium and a hydrogen on the left. So is this carbocation going to rearrange? No. Did we form a stereocenter here? Yeah, because deuterium and hydrogen are different identities, and so we would have an RS assignment. So what that means is we're going to have stereocenters at both of our carbons, so we need a representation that's going to account for all four diastereomer products. So I'm going to do one where I add the H and the Cl on a dash. And that's going to be our syn product. Now I can do plus and minus for the other syn. And then we have the version where one of them's on a dash and the other one's on a wedge for the two things we added. And this is our anti-version. I'll highlight here the two things that we added. Yeah. So I'm drawing this very explicitly in this way to show the syn and anti really clearly with the wedges and dashes. But this thing is single bonds. It can freely rotate into a different conformation. Yeah.
Out of curiosity, how would you differentiate the two? Because it's just a tier imagine, but the physical properties.
So with how would you tell it's deuterium versus hydrogen there? So we don't really teach spectroscopy here, but HNMR, deuterium would not show up as a hydrogen on the HNMR. because it has a even number for its like nucleus. Yes, so there is a way to tell with spectroscopy exactly what it is. Yeah. Cool. Okay, so that is our acid addition family. That's our first of the simples. Let's go on to the second family. So this family I used to call the X2 antiadditions, but now I call the halogen antiadditions. I don't have a good name for her. She doesn't have a good publicist. So if you think of a better name, let me know. But the prominence of the word anti in the title should tell you something about what is important in this reaction. So this reaction is going to start off with a dihalide, either Br2, Cl2, or it could even be I2, even though I don't think we explicitly say that in lecture. And what the mechanism is going to be is the first step, the pi CC bond is going to attack the sigma star dihalide bond. And if you put electrons into the antibond, what happens? The bond breaks. So that is this arrow, putting electrons into the antibond, the bond breaks. So then this molecule, this halide, is going towards this alkene, and as you start to form a bond here, you're breaking the bond here, and this is starting to get a partial positive charge. And so the halogen is like, I have some electrons, I'm coming close anyway. Why don't I just donate electrons from my lone pair into your pi star? And so it is putting electrons into the pi star bond, breaking the pi bond, and then using those electrons. It's this kind of cyclical process. So it's fundamentally a different type of mechanism that you have seen from the other ones in the course. And it's going to be one of our kind of foundational classic types of alkene mechanisms. So when you do this, if you had a bromine here, it now has two bonds and a positive charge, so it's a little bit reactive. We would call this a cyclic bromonium ion. And if you had a Cl version, it would be a cyclic chloronium ion. Again, we have names for everything. We're not going to test you on these names, but it's helpful to know them just to give something a name. So what structurally does this look similar to what other functional group? Epoxides that you saw in lecture 7. And specifically, it's an epoxide here where there's this positive charge. So it would be kind of like we did a positively charged epoxide when we are in acid. So when we are doing an epoxide in acid, which side does the nucleophile attack?
Oh yeah.
Yes, backside on the more substituted, right? So here we see our nucleophile for this halogen antiaddition is going to attack backside on the more substituted. Exactly. And so our nucleophile adds to the more substituted side we see over here. And if our epoxide or our cyclic bromonium was on a wedge, then our nucleophile is going to be on a dash because it's doing that backside attack, attacking from below. If it's originally on the dash version, then our nucleophile comes from the top and is on a wedge. So the orientation of the two things that we have added are anti, hence an anti-addition. Now, we have several flavors of this. Like, firstly, we have the bromine flavor and the chlorine flavor. And these have, like, the nucleophile here is just the bromine or the chlorine that you kicked off. And so you have this vicinal dibromide. And we would say it's vicinal because they're in the same vicinity, like they're right next to each other. But if we have a solvent, something different happens. So look at this case down here where we have the Br minus from the first step, but we are in water solvent. Who do you think is going to attack? One bromine boy or one of the millions of like armies of water molecules? The water. And so it's going to come in and do the backside attack. So for our solvent version, it is the exact same mechanism, but instead of a Br attacking here, it would be our OH2 water, and then you would have a deprotonation. I mean, for the specific reaction, you need to say what the specific solvent is. Because, like, sol we can use when we don't care about what the identity is. If it's adding to our molecule, we care about the identity. So we can do this with water, and this is kind of the water flavor, where the thing that we form is a halohydrin. What are halohydrins? What do we remember about lecture 7? What do they do? They can form epoxides. So if we add like NaOH to this, this can form an epoxide. We can also do this with an alcohol solvent. And when we do that, we get this thing called a halo ether, where you have the OR from the alcohol added in that position and then the bromine in the other. Notice also that here, when you are comparing like what added to the more substituted side, you have an oxygen versus a bromine. Which one's more electronegative? Oxygen. Did it add to the more substituted side? Yes. Yeah.
I don't remember, but like I see it as big nucleophiles.
It's not really about nucleophile strength, it's about numbers. It's about you would have one of these and you would have moles of the other. Yeah. Cool. So let's try some practice. There's this weird skill builder one where instead of doing Cl2, we're doing an ICl bond. It's still a dihalide, but you have to ask yourself, which one is more electronegative and how do I get it on the more substituted side to follow Markovnikov's rule? And as a hint, I have told you a note, chlorine is more electronegative. So somehow chlorine needs to be on the more substituted side. The thing you'll have to figure out is, does that mean that chlorine forms a cyclic ion or does iodine? Don't say it out loud. The other one that I'm going to do over here is one that I'm just making up. Try to predict the product of this reaction. So take a couple minutes.
Would you also say that a lot of these models are valid?
That's
like for like certain.
Mm-hmm. Yeah, no, I tried to design it to point out patterns. Yeah. So, how'd you do with the skill builder one? So our less electronegative one is iodine. It's going to form a cyclic iodonium ion. And then the Cl minus is going to attack the more substituted side.
What's the more electronegative? What is the less electronegative?
Iodine.
Why does
Oh, I mean, the general explanation is it's further down on the periodic table, and so it has a much bigger valence shell, it has a much bigger atomic radius, and so it's not able to hold its electron as close to the nucleus as something with a much smaller radius could. And so, like, that's part of it. There are some, like, other factors that are a little beyond us, but that's kind of the biggest one. But truly, it could just be thought of like electronegativity trend, chlorine is here, iodine is here. Yep.
Why did you not repeat the series?
Do we have any stereo centers? So we don't care. Yeah, it's the nice thing where a lot of these will end up being easier stereochemistry-wise than you would expect. Okay, yeah,
I think kind of silly, but like, how do you get that drawing? Like, I struggle with the drawing.
just this.
Like the pseudo-epoxide. Like I
I mean, if you wanted to draw it like, that's fine.
Who puts that in?
Let's put other thing.
That it's,
Well, that's a separate question. That's the next one.
Oh.
So, for this one here, we are going to form a cyclic bromonium, just like we did with all the others. And now this is the weird step. So you might remember being burned in the past on the problem set from a long molecule where there's like an OH way on the side. What happened in that case where you were caught off guard? An intramolecular reaction. So yes, we do have a Br minus round, and yes, it could hypothetically do the attack here and we get the dibromide. But a much faster reaction would be a molecule reacting within itself. And so this OH could come and do a backside attack, kick it off. And so I'm going to do these kind of two arrows here to just be like, hey, I'm not drawing everything, and I'm just drawing this kind of key step. But when we do this, we would form a 1, 2, 3, 4, 5-membered ring. One of them is an oxygen, so that's we know is in our product. And then if I number 1, 2, 3, 4, 5 here, we have a dangly bit off of carbon 1. We still have this carbon and this bromine. So on carbon 1, we have a carbon and a bromine. That is a stereocenter, so we would put it on a wedge. And then we would do plus minus because both are options. And technically I should have written plus minus here in this step because we could have formed the wedge version of the cyclic bromonium, or we could have formed the dash version. So these are kind of the intricacies of that second big family with the X2 anti-additions. And do you see how the mechanism is just like fundamentally different from the acid addition ones with the carbocation? Those are kind of our two big mechanism families. And then the third one is not quite like a big mechanism driven one, but is more kind of like a concept that you want to be able to do with alkanes. And so the third family that we're going to talk about are making alcohols from alkanes. So the issue is this thing that we saw with the mechanism on the previous page, where if we add H3O plus to this alkene, we would get Markovnikov addition, but with rearrangement. We want the ability to do two different things. We want the ability to do Markovnikov addition of an alcohol without rearrangement, so that's one thing that we're trying to do. And the other one is we want to be able to do anti-Markovnikov addition, where we add the OH on the less substituted side of the double bond. So let's meet these new reagents. So to do Markovnikov without rearrangement, we use mercury. So the HgOAc2, H2O. And our second step is NaBH4. And you might be like, NaBH4, I remember her. NaBH4 methanol. I know the reaction. This NaBH4 is doing radical things. It's weird, so you are not responsible for that. But this is the, I always forget, oxymercuration reduction. Then, for anti-Markovnikov, we use hydroboration oxidation. So it is BH3 with THF, and we have H2O2 with OH minus. That's our second step. So the way I'm introducing this really emphasizes the line reactions, and it's because this is going to be really important for synthesis and for box problems. So you will really need to know that. We do go into some detail on the mechanisms, though, for the first steps of both of these, and so let's talk about those mechanisms and why we get no rearrangement and why we get anti-Markovnikov. So for the oxymercuration, we would start off with this HgOAC2 here, and you would have the pi CC attacking the sigma star mercury oxygen bond. It breaks the bond. And then you would have a lone pair on mercury attacking the pi star CC. And then here, we would call this the cyclic mercurinium ion. Now, does this type of structure look familiar? Like, in terms of this, where you have a three-membered ring with something positive, where have we seen that before? Yeah, the ones right before this, the cyclic bromonium, the cyclic chloronium ions. So it's a really similar first step to those halogen anti-additions. And also, just like the cyclic bromonium, cyclic chloronium, and the epoxide and acid, our nucleophile is going to attack on the more substituted side. So in this case, our reagents are HgOAC2 and water. And water now comes in as the nucleophile that attacks over here. And we would get this intermediate. Now in this intermediate, we would have the OH and the HgOAC added here. And this would be an anti-orientation. One's added on a wedge, one's a dash. But when we do our second step, this reduction with NABH4, because it does stuff with radicals, that is going to scramble the stereochemistry. And so our final product, we are going to get the version that is anti, and we're also going to get the version that is syn. And technically, these should have plus minuses for both of them. So sorry about that. I also put a skull and crossbones on this because, like, organomercury compounds are the ones that they, like, warn you about in the lab safety videos that, like, scar you for years afterwards. Like, there was this whole story about this, like, leading chemist who had a really promising career who got, like, half of one drop of, like, organomercury on, like, literally right between her glove and her hand, and then was dead within 2 weeks, and, like, the neurotoxin of organomercury compounds, like, lost mobility. She knew exactly what was happening to her, and, like, as soon as she saw it, she was like, okay, I'm gonna die. Horrible. Horrible. So you will never do this reaction. You will only do this reaction on paper. And there are now better ways of doing this, but this is the kind of classic way in terms of if you are a hardcore chemist and if you have all your PPE, you can do it. But scary stuff, scary stuff. So here, why do we not get rearrangement? Well, we don't have a carbocation. And so if we don't have a carbocation in this whole mechanism, we're not going to have a rearrangement. So that's the nice part about it. The other thing that you'll notice is over here we have kind of a second flavor of this reaction. We have water, which is our basic one, but we can replace water with an alcohol, and then the thing that would attack here is an alcohol. So what we would get at the end of the day is an OR added. We would have made an ether. And that, folks, is our final way of making ethers. Aren't you so glad you know all of the ways to make ethers? Ethers are my least favorite functional group. I just can't. So this is also where you go ahead. Mm-hmm. Well, but it's not attacking from below. This is attacking from below. Remember, arrows are showing movements of electrons. They're not showing the trajectory of the molecule. So we know that this thing must have attacked from below because our bond that we're breaking is on a wedge. And so, like, imagine if our bond was on a wedge, it was kind of going up, then our antibonding orbital is going to be below. And so our nucleophile is coming from below to break it. Yeah, totally. So this is the part where I'm going to give you my, like, silliest, most basic, most smooth brain mnemonics for the whole class. And you're really going to, like, lose respect and be like, they have a degree from Harvard? So, with remembering no rearrangement, what reagents to use, and knowing to use mercury, I think about astrology. And I think about, like, someone asking you, oh, do you want to go to this thing and, like, change your plans? And I'd be like, well, my Mercury's in my 7th house right now, so I really shouldn't rearrange my schedule. I should stay the course. And so Mercury doesn't rearrange. That's it. Like, Mercury's in my 7th house. I don't want to rearrange my schedule. I need to keep that alignment. So really, really smooth brain. The hydroboration oxidation one is even smoother. So hydroboration oxidation for anti-Markovnikov, this is commonly abbreviated as HBO, hydroboration oxidation. And what's on HBO but movies? And specifically the 2006 movie John Tucker Must Die, where they don't like John Tucker. One might say they're anti-John, in which case they might also be anti-Mark. And so really the way I think of it is I need to do anti-Markovnikov, anti-Mark, anti-John, John Tucker Must Die, HBO, hydroboration oxidation.
Yeah.
So I don't know if that's helpful for you.
I feel like it's so preposterous that I'm
That's the thing, like it's so outlandish.
that, like, it works.
But again, you can also just do flashcards, but that's less fun. Cool, so let's talk about how this adds anti-Markovnikov. So the first stop, you start off with BH3, and what happens is your double bond's going to attack the empty orbital on the boron, and then this sigma bond is going to go and hop over to the alkene. And so, like, if we were to write out the orbital interactions, they would be pi cc to the 2p boron orbital, and then sigma boron hydrogen moving over to the pi star cc. Now, when that happens, you now wind up with a hydrogen and a BH2 added on the molecule. And those are going to be added syn, either both on wedge or both on dash. It's kind of like if our alkene was here and the boron's approaching from above, both things are going to have to come from above because it all happens in one step. If the alkene's here and the BH3 is coming from below, both things are going to have to add below because that's just where they are. It happens in one step. So now, if you were to look at this, on a first glance, this would look to be anti-Markovnikov because you've added a hydrogen to the more substituted side. But if you bust out the Pauling electronegativity values, boron has electronegativity of 2.04, hydrogen's 2.2. So hydrogen's more electronegative, and it's adding to the more substituted side. Does that follow Markovnikov's rule? Yes, it does. So this step totally checks out with our version of Markovnikov's rule. So that's fine. And then step 2, the oxidation, where things get a little bit weird, where all that you need to know, because you're not responsible for the mechanism of step 2, is that BH2 is replaced by an OH, and it retains that syn stereochemistry. Also, like HBO, it has like the ratings where like it will have cursing and nudity and things, and so there's a lot of syn on HBO. But, so with this, we see overall this process, if we looked at the two things final on the molecule, it looks anti-Markovnikov because our OH, more electronegative thing, is over here. But in the key step with the alkene, it still followed Markovnikov's rule. So that's kind of the logic of like how it works and why overall the process is anti-Markovnikov. These reagents, it is a lot to just kind of regurgitate them. BH3THF, H2O2OH minus. Like there's like a trauma like response ingrained from like when I took this 9 years ago or whatever. Cool, so that's the second one. This is like an FYI thing. It's truly none of it's tested, but I think that the mechanism of the second step is really cool. And you technically saw it on PSET 1. We gave you the structures and you drew curved arrows. But this is just some more facts about boron chemistry and things related to this that I think are interesting. None of it tested. So with that, let's try this practice where you're drawing the mechanism of the mercury one. But the tricky thing about this one is instead of water, we have methanol here. Then you're drawing the mechanism of the first step of the hydroboration oxidation. But the weird thing here is instead of BH3, you have BD3. So deuterium is going to be used instead of hydrogen. And then the last one here is like a 2 to 3 step synthesis from the challenge problems, where you're just going to try to make the product from the starting material. So let's take a few minutes for this. The first step you are.
Oh.
The second step you are not.
Like if you were trying to make this structure instead of the final
Whenever we do that, right before the class, we get rid of these.
Yeah, I remember.
You get rid of what?
And I think it's,
I mean, so intermediate part of the path, one of the comments.
but to get to two. I know it's
That's the step two. Step two replaces the HTML with just an object.
uh,
Do you want one more minute or two?
Oh, for, the first one or all?
For all.
And then it's really just trying to want to see this pattern. Really Oh, that's
Okay.
yeah.
I did not do that.
Where, yeah, I don't really care if you go back to this.
So I think I'm just going to copy from 10 a.m. here. So, for these, it's kind of just for the first steps for each of them, regurgitating the arrows. Stereochemistry can be a trickier thing, but one kind of hint for this first one is if you look at the product and don't see stereochemistry, then that means you did not have to account for stereochemistry for the question. On exams, you will be very explicit of like, take stereochemistry into account, or don't, or you may ignore stereochemistry. You will see one of those statements on the page. So for this one, I just drew the like wedge, cyclic mercurinium ion, and then attached, and then it's on dash. And I drew this as a wedge and a dash just to again emphasize that these are added anti. But is this thing over here a stereocenter? No. So wedge or dash doesn't really matter. And then we deprotonate it, and that's the mechanism for step 1 that you're responsible for. Step 2 replaces the OAC with a hydrogen. Then for the BD3 version of BH3, it is just the deuterium, which is more electronegative, adds to the more substituted side over here. So we would get the BD2 added to the other side. Again, I just did wedges on both to emphasize that it's syn, but are either of these stereocenters? No, this one has 2 hydrogens, and then that molecule is the same on either side. So those are equal. So it's just kind of tracing those on. For the bottom one, what 2 things needed to be added to the alkene here in the product? Like, what are the 2 new atoms that are present? A Br, and then what else? An H, great. So we need to add a Br and H, and is this adding Markovnikov or anti-Markovnikov? Anti-Markovnikov. So the only reaction that we've talked about that does anti-Markovnikov so far is that hydroboration oxidation. So let's try that one out. So that would add an OH anti-Markovnikov, and it's the BH3, THF, H2O2, OH minus. Okay, well, do we know any reactions that go from an alcohol to a bromine? From lecture 7. Making alcohols leave. PBr3 is going to be the easiest one. It replaces the OH with a Br. And so that's how we could do this, as like a little mini synthesis. Now, you might be like, well, Colton, towards the end of class, we learned about HBr ROOR as doing an anti-Markovnikov bromine addition. This, if we did not have this strained ring right next door, that would be a valid path. But because it's a strained ring, you would actually get some weird stuff going on with the radicals where the ring would open. And we're going to actually do that on section on Friday. So we'll kind of see that kind of nuance and what's weird with that. But that's not going to be a valid path for this one. Yeah.
Why doesn't the ring open here? Oh, it's
You don't form a carbocation. Yeah. Cool. Okay. So I'm torn on time. All of the other sections have been about 8 minutes over, and so let me kind of present the 3 last things that I would talk about and then give you a choice of what y'all want. So, one is there's these tricky alkene stereochemistry problems, and maybe I'll give you just like the headline so you know what the type of problem is. It's one where you're given a product and the reagents, and you have to make the reactant. And here, this D2 palladium on carbon, that's like H2 palladium on carbon. The 2 things it adds are 2 deuteriums in this case. And this is a reaction that's like syn. So we see that the deuteriums are added here. So we know that the double bond needs to be right this. The tricky part is it going to be this alkene, or is it going to be this alkene? Like, what is the stereochemistry of this, and how do we reflect the fact that this is a syn reaction? And that's like a really kind of tricky conceptual thing. But to be very honest, that will be one box problem on the test. And if you got the wrong alkene, it's 2 points. It's not going to be, like, part of me is like this, if we talk through all of it, it will take about 10 minutes. And I think it's good to understand it, but it will take some time. So that's kind of this first topic. The second topic is the complex reactions, where I'm going to touch on like 3 of these: ozonolysis, osmium tetroxide, and epoxide formation with MCPBA. We'll do a little disconnection. That's like about 8 minutes total. And it's just kind of highlighting the ways of thinking about complex alkene additions that are more line reaction. And the last one that we have to talk about is the Wittig, because it is one of the most commonly tested mechanisms and synthesis box problems. It's maybe the most important reaction we are teaching you for the second exam, I would say. So you really want to know the Wittig, or Wittig, not Wittig. So between those, I did talk through this in my 10 a.m. section and have a video of it. But I guess the thing that I want to see is, like, do y'all want me to do this with y'all here and try to do it kind of quickly and talk through it, or do you want me to skip this so that we can get to everything else? I could, and that would be faster. Yeah. Again, I'm going to be posting all the videos now, just, yeah. Okay, so let's talk through this because we've already started to set it up. With our reaction here, we know it's syn, and the way that it is currently written, these deuteriums do not look syn, right? Like one looks in the plane, one looks on a dash. There are several methods that you could use to deal with this, and I'm going to show you my preferred method. So my preferred method is, if the two things were added syn, you draw them in the plane going the same direction, and then look at the wedges and dashes once you've rotated it. So over here, this deuterium is already in the plane, so we can just draw the dash methyl exactly as it is, and the hydrogen wedge. But this one on the bottom over here, this deuterium is not in the plane. So it's like the deuterium is down going away from you, and you want it to come down in the plane. So from here to here. So when we do that, what happened to the methyl that was here? Well, it's going to rotate from here to here. It's still going to be towards you, but it's now going to be up and on a wedge. And finally, the ethyl that was in the plane, you're going to be rotating it now back. So the ethyl is going to be on a dash. This is the thing that I was going to have y'all try to do with models to kind of see it. But I will do that with the model in a minute. Once you have written it in this way, where you see the stereochemistry with the things in the plane of the reaction, then whatever is on wedges is going to be cis to each other, and whatever is on dashes is going to be cis to each other. So we know that the hydrogen and the methyl have to be cis to each other. So over here, we have hydrogen and methyl cis to each other. So this is the one that's our actual starting material, and it's not that one. And we also see that the ethyl and the other methyl are cis to each other. Let me build it really quick and kind of show you the model kit version of it.
Yeah. I figured.
Oh, yes, sorry.
Where did we get that?
Yeah, let me clean that up a little. Ooh. So, I have built this molecule here, and the way it is on my model kit is I am putting the deuteriums in blue, and I am putting the methyls in red. So, here I have a deuterium that's in the plane, and here I have it down and away from you. And then the methyl up here is going away from you, dash, and it's coming towards you over here. Do you agree with me that this is going to represent that, and we have the correct placement of our deuteriums and our methyls? So the rotation that we did to get over here, if you do it with a model kit, it's literally this. And you see how when we rotated it, the methyl over here is coming towards you, the methyl over here is going away from you. So it's easy to see, but even more than that, more than helping you rewrite it, when you are doing a syn reaction and two things are in the plane, you can just fold them in and see what that alkene would look like. And do you see how the methyls are trans to each other? The methyls are trans to each other here. The one in green and the one in yellow. So there's a way of doing it with your model kit that can help you. These are like lots of strategies for it. I think having the paper version or a model kit version, just anything that works for you is helpful. But again, we're talking about the difference between 2 points versus, hey, I wrote that answer initially super, super quick, right? Like I got these 2 different versions in like 10 seconds versus everything else took like 5 minutes. So it might just not be worth it time-wise. But let me do one more example to show you. So I2, we would look at the reagents. What 2 things does this add to the double bond? I and I. And does this add in a syn, anti, or mixed faction? Bless you. Okay. I2 is going to be like Br2 or Cl2, so is it going to add anti? So for anti, we want our I's to be in the plane, one going up, one going down. And hey, that's how the molecule already is. So we didn't even have to rotate this one, which is nice. So here we see ethyls on the wedge and a hydrogen on the dash. So doing the same kind of system with the highlights that we had before. We have our things that are in the plane, which were what was added by the reaction. We have our wedges, green here, that need to be cis to each other. And we have the hydrogens, yellow, that need to be cis to each other. So to draw the product, you would do ethyl cis and the hydrogen cis. The hard part really is that kind of when you have to rotate seeing it. Because if we write it in a nice way, it becomes an easy problem. So I'm going to let you do the other one, which is, again, these are all challenge problems. I'm going to let you do the other one for practice and try working out, try using the video. But I'm going to go ahead and move on so that we have time to talk about everything, okay? So first up, we have ozonolysis in our complex alkene additions. And this is definitely going to appear on both exam 2 and the final. It's a really, really common reaction for both line reactions and synthesis. And the big thing that you need to be able to do is you need to be able to just write the products. So this is one where you are not responsible for the mechanism. Tim showed you a mechanism for the first step, but we've never asked anyone to reproduce that. So the fake mechanism of how to just draw the product is you're going to cut the alkene in half and stick a carbonyl on either side. When we do that, this we call the reductive product. So that just cut it in half, put a carbonyl on it. And we can tell if we are in reductive conditions or oxidative conditions by the identity of our second step. So if our second step is H2O2, we're in oxidative conditions. And if it's dimethyl sulfide, we're in reductive conditions. So if we were doing DMS and we had cut it in half, we would be done. This is our product. If we were in oxidative conditions and had H2O2 as our second step, the only thing we would have to change is if one of our carbonyls was an aldehyde, which this one is, there's a little hydrogen there, we would then have to make that aldehyde into a carboxylic acid. And so just change it out with an OH. And that's all it is. So let me do an example, one of these with y'all, and then I'm going to have y'all do the others. I'm going to do the middle one because it looks a little bit weirder. So do you think ozonolysis is going to happen on a benzene ring? No. Have y'all learned any reactions of benzene rings? No.
The NPPR problem.
But that's not in the ring. Yeah. You will learn benzene reactions tomorrow. Ooh. Excitement. But this is the only one that's going to do our normal alkene reactions. So we are going to cut this in half and put a carbonyl on either side. And try to draw it.
I think this should be actually.
This alone.
Yeah,
Yeah. Yeah. I mean, this will certainly be part of a question on the exam. So here, just chopping and putting the carbonyls, that's our reductive product. To get to the oxidative one, I'm going to copy and paste. And where there was a aldehyde, I'm going to now make a carboxylic acid. So can you try on this top one and the bottom one? And I'm going to truly give you a minute. So how'd you do? So chopping in half, putting on carbonyls, oxidative conditions, you need an OH, reductive, you just need an H. Then down here, when you chop in half, both of them are ketones, so there isn't going to be a change between your reductive conditions and your oxidative conditions. So that is ozonolysis. That's kind of the big scale of being able to predict the product and then to know whether or not you want to use reductive or oxidative conditions and how those would be different. Osmium tetroxide, these reagents are a bugaboo. This is my least favorite one to memorize, and I always forget the second step. It's this NaHSO3 H2O. You don't need to know the mechanism for it, so like it's really easy to forget, and it's just kind of a memorization thing. But this forms a vicinal diol, also known as a glycol. So two OHs. And the important part about it is it forms the two OHs syn to each other. Now you learned in lecture 7 a way of making a vicinal diol where the two OHs were anti. What was that? The lecture 7 way of making a vicinal diol anti. It was an epoxide, and we could do it either in acid or base, depending on which one we started with. So it was an epoxide here with either NaOH or H3O+. So the epoxide opening makes the anti version, and then the osmium makes the syn version. Again, you don't need to worry about the mechanism at all. Even though we showed the first step, you don't need to worry about it. Between these two, let's say I wanted to react with a ketone, and I have a diol. What functional group would I make? Acetal, all the way back from lecture 3, of a ketone plus two alcohols makes an acetal. Which do you think would be easier to make an acetal? Syn OHs or anti-OHs? Syn. And it's because when we make it, we would have the two O's bonded here, and they're both still going to need to have that syn orientation, where here we could have the rest of the ring. Oh, that looks ugly. But Here, it's kind of like if your OHs were going the same way, it's going to be easier for them to meet in the middle and form a ring, up, meet in the middle. Whereas if one was up, one was down, it's going to be hard to like go around. And so that's something to keep in mind. This is like historically been a great way that we throw back to the acetal reaction of making a diol and then doing something with a ketone or aldehyde. So last one is one of my favorite reactions in this class, which is epoxide formation from an alkene. So this uses a reagent called MCPBA, and I just like it. I think it's neat. I think it's cool. I'll talk a little bit more about why I like it in section 9 once we talk more about some benzene things. But like, this is just a fierce reaction where you have 4 arrows in one step and then the whole thing's done. Like, this is the full mechanism of the reaction. And it gives the energy of like a gay person who's very busy, who's like, I just need to get this done. And like high energy, lots of stress. And then you're an epoxide, which is the explosion molecule that's high energy, lots of stress. I just like it. So this is now the second way you know of making epoxide. What is the lecture 6 way? Or sorry, lecture 7 way.
Oh, it's the OH thingy with the BR. That's called.
The halohydrin.
Ooh, what's a dimer?
2 alcohols.
Ah.
Yeah. So you could do halohydrin with NaOH, and that would make an epoxide. So those are going to be all the ways you know to make an epoxide for this class.
So there's
Those 2. Yeah. So that's the kind of complex reactions. And shoot, even with abbreviating it, I'm going to go 4 minutes over. But let me kind of jump into Wittig. There are some reactions I didn't talk about that are not on this section handout, but that are on the big section web. So the carbanoid additions, I just don't care about them. The H2 palladium on carbon, you don't have a mechanism. It's syn. You add 2 hydrogens. And then radical bromination we'll talk about in section 9. So, so it's fair game. It's never been asked. So I would probably not worry about it. The Wittig, oh, sorry.
Sorry. Can I just give you a question?
Okay. So the Wittig reaction. It looks like Wittig, but it's Wittig because Germans, their W's become V's. And the key idea here is the Wittig reaction is a powerful way to make a CC single bond and an alkene at the same time. So making carbon-carbon bonds for organic chemistry is kind of a difficult task. You guys only know like 2 or 3 ways of making a carbon-carbon single bond. And then the fact that it can also make an alkene, which you only know E1 and E2 to make alkenes, it does all of that at the same time. It's really, really a powerful reaction. It will be on a mechanism or a synthesis question, full stop. Like you are definitely going to need to know this well. I call this reaction the Boxy-Boy reaction because at a key point in the mechanism, you form a box, and that's just kind of cool. Tim calls it the switcheroo or something, to each their own. The Wittig reaction takes place between a ketone or aldehyde and this new functional group called an ylide. And here this is a phosphorus ylide where we have the PPH3 plus right next to a carbon minus. So line reaction-wise, our kind of fake mechanism is we glue whatever is attached to the carbonyl or the phosphorus together with a double bond. So the one part that's a little tricky is there's a hydrogen still on this carbon, and so that's where we get the R2 and the hydrogen, and the R1 and hydrogen come over here. And we could have also had a ketone, in which case we'd have 3 things. Notably, this particularly likes to form Z alkenes, and we're not really giving you a good reason. It's a little bit complicated. The only thing that you need to know is Wittig forms the Z alkenes. So one thing that this does really well is it makes terminal alkenes, so alkenes on the end of a molecule. Why was it hard to make terminal alkenes for E1, E2? Y'all are saying a lot of the right ideas. I might summarize all of that in Zaitsev's rule. So Zaitsev's rule is it was more favorable to form more substituted alkenes. So if you had like a leaving group here, bromine, you would want to form this alkane because it's more stable, rather than this terminal one. With the Vidic though, depending on where you kind of cut here, you could just make this either your aldehyde or your like ylide, and then it's super easy to make a terminal alkyne, or alkene now. So here, like this is CH2, you have CH2. So this carbon right here could become the end of the molecule here, and the rest of it is from the ylide that's glued on. Or you can make that carbon the ylide of a CH2 minus ylide, and then the rest of the molecule is the carbonyl that you're attacking. So just something to like flag as a common thing that you will see the Vidic do. That's the only one that y'all need to know. So now, if you're doing a synthesis and want to do a Vidic reaction, you are allowed to pull an ylide out of thin air. You are allowed to invent an ylide, write it down. But if you want to take a molecule you currently have and change it into an ylide, you need to know how to do that. And this is something that both line reaction and mechanism you need to know. So what happens is the first step, you start with an alkyl halide, which you now know many ways to make alkyl halides from alkenes, from alcohols, lots of ways to get to this. And then you add PPH3. This has a lone pair, and it's going to do a backside attack, SN2, and kick off the bromine. Then it's going to have a positive charge here. We are one step away from being the ylide. We just need to remove a hydrogen next door. And so we use N-butyllithium, which acts as a strong base. We always use N-butyllithium standardly for the Vidic reaction. You could potentially use other bases, but like this is the kind of set way of doing it. Just like for Williamson ether, we used NaH as our base there. So that is the formation of the ylide. It's these two like one-step reactions, which is really kind of straightforward. The actual Vidic mechanism starts here once you have your ylide and your ketone or aldehyde. So the ylide is going to be your nucleophile, and it's going to go and attack the pi star CO. Then you're going to wind up with an intermediate structure where you have an O with a negative charge on an adjacent carbon to the PPH3, which has a positive charge. And it's just going to scooch over and make the box. So at this point, it does this kind of really cool arrows trick where the box is going to collapse. The electrons in this CO bond, which you're trying to get rid of, they go and form a double bond between oxygen and phosphorus. And the electrons in this carbon-phosphorus bond, which you're trying to get the phosphorus off as well, fold in and make the double bond here, the alkene. And so what you wind up with is the alkene, this Z1 preferentially formed, and then this byproduct that has a PO double bond. This is a little weird because it's phosphorus chemistry. Like here, this phosphorus has an expanded octet. And well, go ahead. So this arrow, the electrons that were in this carbon-phosphorus bond are the ones that are now in the double bond. Yeah. And yeah, I don't know, this kind of just like folding of electrons, satisfying. Like ASMR, but mechanisms or something. And no auditory, silent ASMR. So the last thing here is this synthetic disconnection practice, because that's going to be a big skill to be able to use this and visualize the products easily. So I'm going to do the first one with you. We know that to undo this and get back to what the starting materials were, this reaction makes this alkene. So we need to break it in half when we are doing our disconnection. And we have two options for how to disconnect it. I'll call them option A and option B. So option A is we can make the top part of this double bond our aldehyde or carbonyl, in which case it's formaldehyde here, that has two hydrogens. And then that would make the bottom our ylide. So that's one option, the top carbonyl, bottom ylide. The other option is make the top one your ylide. So PPH3, and that's with CH2 minus. And then make the bottom one your carbonyl for the C double bond O. And a question that we like to ask that's kind of associated with this is which of these combinations would be the better synthetic route? And the answer to that has to do with the formation of the ylid. So do you remember in this mechanism step how we had an SN2 attack here, where we had to do a backside attack on the alkyl halide? Well, what type of alkyl halides are good for SN2? Primary and methyl, and then secondary gets worse, and tertiary is almost impossible. So, if we go down here, this is an ylid that's secondary. This is an ylid that's like methyl. So left, or option A versus B, which is going to be the better route?
B.
B is going to be the better route because this ylid is much easier to form. It's really easy to do the backside attack of CH3Br, and PPH3 just comes from behind and kicks off the Br. So, what I think we're going to do is I'm going to leave this as an exercise. If you want to stay after and do it on your own and like check it, you're welcome to. Otherwise, it's going to be in the video online that you can check with and in the annotated version. So thank you all for coming to section. Thanks for letting me go like 5 minutes over here. But I will be sticking around and answering questions. And again, if you want to just do the little disconnection and check it real quick, you can. So thank you. Whew. I've really been in this room since 8 a.m.
Your last section?
Yeah. Oh, God. Bye. Have a good day.